Hi everyone, thanks for the opportunity. This is Jingliang Dong from RMIT University. My today's research topic is vortex identification and its influence on particle exposure characteristics in a realistic human nasal airway. In the next few minutes, I will talk about the research background, methods of this research, and results and its potential contributions to the field. So let's start. Okay, let's start with research background. The air around us may appear to be clean, but it carries many types of microscopic particles, such as dust, viral droplet, and pollen, that are not visible. Those particles can be breathed in and are then trapped on mucus in the nose, throat, and lungs, where they can cause infection. Among all potential adverse consequences, chronic rhinosinusitis, or CRS, is a common nasal disease that can cause a series of nasal disorders, including the symptoms of nasal obstruction, nasal drainage, decreased sense of smell, and etc. According to statistics, in each year, approximately 30 million adults living in the US are suffering from this specific chronic illness, which can subsequently bring in an annual economic burden around 22 billion. Apparently, the air particle flow plays a dominant role as it determines the particle transport behavior as well as the fate of inhaled substances. Existing research studies are primarily concentrated on the interplay between the air particle flow and the respiratory airway, where dominant deposition mechanisms are inertial impaction, gravitational sedimentation, and diffusion. However, the presence of vortex structures and its effect on particle deposition remain significantly less studied. In this study, a newly developed vortex identification method, LUTEX, was utilized to properly extract the local flow vortex structure within a realistic human nasal airway. So this slide illustrates the computational model and the and the setup of its boundary conditions. Specifically, a pressure inlet and velocity outlet conditions were adopted, and the breathing zone was added to capture the realistic flow fields near the nostrils. After everything was properly set up, the continuity and momentum equations were solved by using ANSYS Fluent software. In addition, to establish a realistic breathing pattern, a transient inhalation and exhalation breathing profile was adopted, where 3 time events, T1, T2, and T3, during the inhalation phase were selected for data analysis purposes. So the most contribution of this study is the vortex structure identification by using the LUTEX method. Although the conventional index of vorticity is a vector as well, vorticity is contaminated by share. In other words, some share is misunderstood to be included as a vortex. Compared with the current vortex identification methods, LUTEX has a clear physical meaning. That is, the direction of LUTEX indicates the swelling axis, and the magnitude of LUTEX represents twice angular speed of the swelling motion. So now let's talk about the simulation results. This slide compares the streamline patterns of 3 time events. Generally, all 3 time events exhibit similar flow patterns. That is, flow acceleration occurs shortly after being inhaled into the nasal airway due to the reduced airway size in the vicinity of the nasal valve. Then most of the air currents were conducted through the middle to inferior portion of the main passage. Notable flow separations can be found at the anterior upper portion of the nasal airway, as highlighted by the red circles, which may lead to an extended residence time for inhaled particles. This can pose additional exposure risk to the airway. Besides the streamline results, these slides provide quantified vortex structures under the initial and peak time events. As I introduced in the methodology slide, the magnitudes here directly reflect the angular speed of the swirling motion. Here, isotropic surfaces were used to facilitate the three-dimensional visualization, where green surfaces stand for vortex structures with a Lutex magnitude of 500, and red surfaces stand for vortex structures with a magnitude of 1000. Interestingly, despite the time difference, similar vortex structures are found from both the T1 and T2 events. That is, vortex structures or swirling flows are predominantly occurred in the space corresponding to the vestibule and anterior middle meters. Therefore, it's anticipated that enhanced particle deposition may occur in close vicinity to these identified vortex structures as a result of transverse diffusion effect due to the presence of secondary flow. This slide concludes this presentation. In this presentation, a transitional numerical simulation of inspirational airflow was conducted in a realistic adult human airway. Our results, despite the airway undergoes velocity magnitude changes, the primary flow patterns remain relatively stable. Our results show strong swirling motion were identified by Lutex magnitudes and were predominantly, and those structures were predominantly concentrated at the root of the middle meters. This may lead to enhanced particle deposition in close vicinity to these identified vortex structures. Following studies that includes nano and micron-sized particles, transport and deposition analysis are underway. Thank you, and any questions?